Okay, so obviously humans are really good problem solvers. Just look around in your environment right now and see all the problems that we have solved, like how to provide shelter for ourselves and things like that. So I'm not trying to say we are not great problem solvers, but there are things that in any given situation where a problem confronts us, we may not be as efficient or as effective as we might want to be. One thing that interferes with our problem solving capabilities is the confirmation bias. The confirmation bias is defined as the tendency to seek information which supports our beliefs and to disregard contradictory evidence. We really like to think we're right. we really like to think we already know the answer. We think our opinions are valid and that any logical person would hold the same opinions we do. It's just how humans are. And so one of the things we do to maintain that belief that we're right and that we have the right opinions and stuff like that is that we only seek out information that confirms what we already believe. And that way we never have to confront the possibility that we're wrong. Sometimes we have to confront it because it comes after us, but most of the time we disregard contradictory evidence. Even when it's put right in front of us, we are convinced that it is wrong. It has to be wrong. In regular life, our natural tendency is to say something like, if I'm right, then fact C will confirm my theory, so I'm going to look for C. I'm going to look for the fact that will confirm my theory. That's what we do in our normal life. In science, what we say is, if I'm right, then fact D will disprove, or at least disconfirm my theory. So, in science, we search for fact D, the one thing that could show us that we're wrong. The fact that humans can think scientifically obviously shows us that we can do it. But in our everyday life, we want to find fact C that will support us. We don't want to find fact D that would show us that we're wrong. Alright, so here's a little confirmation bias test. We've got 4 cards. The A and the D, if we were to flip them over, we would find a 6 or a 7 behind them. And those cards are independent events. So if we flip over the A and we find a 6, it has nothing to do with what's on the D. The D could also be a 6, it could be a 7. So independent events. And then the 6 and the 7 that we're seeing right now have either an A or a D. And same thing, they could both be A's, they could both be D's. One could be an A and one could be a D. So those are the cards that we're going to be dealing with. Okay, now which 2 cards would you turn over to test the hypothesis that if a card has a vowel on one side, then it has an odd number on the other side? If a card has a vowel on one side, then it has an odd number on the other side. Now I always like to set it up with a little bit of, Jeopardy or something where it's like you've gotten a grant to study this really super important question that's being represented by these 4 cards, and your grant is for $20,000 and it costs you $10,000 per card to flip the cards over. So you can't flip them all over. You can't afford to. The max you can flip over is 2. So which 2? Which one, if you feel satisfied with 1? Max, which 2 would you want to flip over? Most of the time people want to flip over A because they're like, well, duh, it's a vowel. Let's see if it has an odd number on the other side. So people want to flip over A. And that's a good place to start because it does have the ability to support our hypothesis, which gives us our confirmation, and we like that. But it also has the ability to refute our hypothesis. If we flip over the A and we find a 6, then we know that the hypothesis is wrong. So A is not a bad place, right? The next most common place people want to go is 7. They want to flip over the 7 and see if there's an A on the other side. That would give us support for the hypothesis. But we have to think about whether it's worthwhile to flip over 7, because if we flip it over and we find a D, that does not refute our hypothesis, because our hypothesis says what should be on the other side of a vowel. It doesn't say what should be on the other side of an odd number. So if we flip over the 7 and find a D, it doesn't refute the hypothesis. So all the 7 can do is support our belief. And the fact that most of us are willing to put our entire grant money, our $20,000 of card flipping capability, into flipping the 2 cards on the table that have the ability to support our theory shows us that we are motivated by the confirmation bias, and it's hard to shed it. And I mean, this is something that obviously you don't care about because I just made it up and it's really stupid. Imagine if it's a high stake issue that you do care about and that does matter in your life, how motivated you are to seek out information that confirms what you already believe. I know I do it. I mean, in things that have to do with my everyday life, I'm always looking for evidence that I'm right. I just did it earlier today when I told my husband what I believed should be the situation ongoing with my daughter in college and my responsibility with regard to her ability to complete more degrees. And it's like, I set up my opinion and then asked him what he thought. And I only asked him because I knew he'd say the same thing I'm saying. I only want to hear what I'm saying. Am I going to go ask anyone else? No. What if they tell me I'm wrong? I don't want to hear that. I want to hear what I think. That's what we do in our everyday life. Now, when I'm setting up a research project, oh, you better believe I set it up in a way where, let's put it this way, I would only flip over the 6 card if this was my experiment. There is no point in flipping over the 7. All it can do is support my belief. I would start with the 6, the one thing that could disprove my hypothesis and only disprove my hypothesis. If you flip over that 6, which is an even, and it has an A or some other vowel on the other side, then we know that the hypothesis is incorrect and we can quit flipping cards. And then we can save our extra $10,000 to put into another study. If I flip over the 6 and I find a D or a consonant on the other side, then I would go ahead and flip over the A. You might as well, because it still has the possibility of refuting your hypothesis. But 6 is where I'd start. I would go for what would refute my beliefs, and that's in my when I have my scientific hat on. When I have my parenting hat on, or my voting hat on, or any other aspect of my life, oh, you better believe I'm looking for evidence that I'm right. That's what humans do. We all do it. But it also makes us ineffective problem solvers because we want to be right. Like I said earlier, we'd rather be quick, but we like to think we're right. And so what we do is we make snap judgments and then believe that we're right, even if we don't have evidence that supports that interpretation. We like to be right. So there's no point in doing the D because it's just there for symmetry, in case you were wondering about it. The D, it's not involved in the hypothesis at all. So go for 6 first. All right. Other problem-solving habits that can interfere with effective problem solving are things like mental set. The word set means expectation. And so you have a mental expectation that the problem is going to be like one that you've seen before. And so as a result, you try out procedures that have worked in situations like this in the past. I think that's part of what's going on with the idiot test and why it works so well, is that they provide scenarios that kind of look like scenarios that the person might have experienced before. And so they try one of the strategies that's worked in that scenario before, even though it's not going to work because they've set it up and it's something weird. Okay, let me give you an example of mental set. This is creatively known as the 3 jugs problem because there are 3 jugs. In each trial, you're given a new problem. And so in each problem, you are told how much volume each jug can hold. Your job is to measure out exactly the amount of water that's indicated in the final column there. In order to measure out that water, there's no guessing or anything like that allowed. You have to fill the jug completely full to be sure that it contains the amount of water that it's supposed to contain. So pretty quickly people start figuring out strategies for how to measure out the right amount of water. Like in this first trial, jug A can hold 21 units, B 127 units, and C can hold 3 units. And you want 100 units left over. You want to have 100 units altogether. So the best strategy would be to fill up the B jug, which holds 127 units, pour out 21 units into the A jug, pour 3 units into the B jug, and then the C jug, throw it out, pour 3 more units into the C jug, and that will leave in the B jug 100 units. Now if you go through this little chart, you'll see that that works perfectly for all of these. It works for all of them. Then we get down here, trial 6. Suddenly something changes. That strategy will still work. We're trying to get 20 units, and we have A holds 23, B holds 49, and C holds 3. The best strategy actually would be to fill up A with 23 units and dump 3 units into C, and then we'll be left over with 20 units in A. But what most people will do in trial 6 is do the same thing that they've been doing in all the previous trials. Fill up jug B, empty it into jug A, empty into jug C twice, and you'll have the right amount left over. And it works, but it's not the most efficient strategy. So people get stuck. And we try strategies that have worked in the past. Even if they aren't the most efficient, even if they don't lead us to the correct answer, we'll stick with strategies that have worked in the past. This leads us very neat and smoothly into the issue of fixation. Fixation is our inability to see a problem from a new perspective. Again, it's sort of that expectation issue, right? You're expecting it to be the same as what you've seen, and you get stuck. So here's an example of an experimental way of testing fixation. You provide 6 matches, and you say, how can you arrange these 6 matches to form 4 equilateral triangles? The first thing most students try is to make a square out of 4 of the matchsticks, and then make an X out of the other 2 and lay it in the middle, and they go, there's 4 triangles, except for they're not equilateral. The hypotenuse is longer than the 2 sides. They're right angles, but they're not equilateral. So there's got to be another solution. Now, in our defense with this particular problem, they didn't tell us that we would be provided with some kind of sticky residue that would make this 3-dimensional strategy work. I was presented with this problem when I was in graduate school, and I felt like a real bonehead for not coming up with this solution. But it only works in 2 dimensions, like drawing it out. It doesn't work with actual matchsticks unless they're sticky. I mean, how are they staying together like that, right? So nobody said we had magic matchsticks or matchsticks that were, coated in honey or something that would make them sticky. Nobody told us we had that. So in my defense and anybody else's defense who didn't think of this 3-dimensional solution, I think it's kind of unfair, because what matchstick would work like that in the real world? But anyway, okay, sorry about the pouting. Okay, how about the 9-dot problem? I'm sorry, I don't want it to be like that. There we go. So the 9-dot problem, don't you love the creatively named problems that we have here? 9-dot problem. We're going to use 4 straight lines to connect the 9 dots. For most people, the first thing they try is basically make a spiral. Starting at one of the corners, straight line down one edge, straight line on and then they try and make that curve, and then they realize that's 5. They go 1, 2, 3, 4, dang it. One too many. The only way to solve this problem is to actually go outside the constraints of the 9 dots. So, like the drawing I accidentally showed a second ago, you'll see that the edges, the points of the triangle, are way outside those 9 dots to get lined up to get in place for the next row, right? A lot of people, we don't think about that. I mean, we all were raised doing dot-to-dot little puzzles and stuff like that. You're not allowed to go outside the lines. You're supposed to be connecting the dots, right? So most of us don't think of that solution. How about this solution? Who would have thought of this, right? You're barely touching some of the edge of these dots. But if you go long enough, and actually if I had a bigger slide, I could have gotten better, the lines would have been more through the middle of the big dots. But the idea of going well beyond the edges of the dots doesn't occur to most people. In fact, when I was in graduate school, I used to work part-time for Wells Fargo Bank in the mortgage lending division, and they had like a monthly newsletter, and somebody, in the monthly newsletter they had this problem, and then the next issue when they give us the answer, the answer was sometimes you have to think outside the box, and they were kind of trying to encourage creativity in their employees and stuff. Most of us don't think outside the box with this. We think you have to be constrained by the dots, and that's part of that fixation. All right. I don't know how long I've been talking because this is such a fun topic. So I'm going to go ahead and stop here and come back with the next segment.